about interstellar magnetic fields and internal structures of black holes. He was a research assistant at the University of Alberta and later a postdoctoral fellow at the University Louis Pasteur in Strasbourg, as well as a CNR fellow and a visiting scientist at Astrophysical Institute, Boston, and University of Miami. He has served as a principal investigator for several observational campaigns with the Telescopio Nazionale Galileo and various fundamental astrophysics projects under the National Institute of Astrophysics and the National Institute of Nuclear Physics. His main research interests include functional normalization in gravity and MHD turbulence models. So, Alfio.
Thank you very much for the invitation. It's the first time in this nice campus. I found this place very nice, and really I think that here science and discussion must be really special, because when you have such a beautiful environment, of course you can have occasion to meet people and have ideas and things like that. So today I'll be discussing about dynamical models of regular black holes. What do I mean with that? You know, the problem is the following. In Newtonian theory, the total energy imagine we have a star which collapses. Eventually, during the collapse, must become negative. So that means that thermal pressure cannot halt the collapse, and the star will continue to radiate an infinite amount of energy into the environment. So that is the picture that we get from Newtonian theory. So in a sense this can be taken as an evidence, indirect evidence of course, for the existence of a sort of a cosmic censorship, because otherwise we will not exist. There will be no life in the universe, okay? So if you use this as anthropic principle, that's already an argument for the fact that singularities in the universe must be somehow hidden. So in Einstein theory, what happens? That the total energy is always positive, okay? That's at variance of what happens in Newtonian theory. But what happens is that the evolution of the star at some point becomes causally disconnected from our universe, provided an event horizon is formed. So you form the event horizon, and that basically is the null hypersurface that saves the paradoxes we have discussed before. The star goes through the event horizon. And therefore, people have started discussing conjectures like under which condition do we form an event horizon? And some people like Israel and Kip Thorne have come with this conjecture. An event horizon will form whenever a matter distribution whose stress energy tensor satisfy some appropriate physical condition collapse until a trapped surface is formed. That's the key point, a trapped surface. And then once the trapped surface is formed, we have singularity theorems from Penrose. What is a trapped surface? How many of you have taken GR courses here? So you know what is a trapped surface, okay? A trapped surface is a closed to space with the property that an arrow beams of light orthogonal to it at any point decreases in area, at least initially, even when it's propagating outward. Okay. So that is the picture that we have in this case. You see in Eddington-Finkelstein coordinate, what is happening. That is the surface of the star. Eventually they will cross the event horizon, and here a trapeze surface is formed. So each the null cone, outgoing and ingoing null cones at each point of the trapeze surface actually points towards a smaller value of the radius. The energy momentum, so imagine that we have an energy momentum tensor given by this expression, and imagine that spherical symmetry is imposed. That is the picture that we get in general relativity. As you can see, at some moment, a singularity must form. So, it's always a good idea to have an understanding in terms of analytical solutions of the Einstein equation. Of course, there are not many solutions of the collapse, analytical collapse of solution. So we'll do the following. Let's imagine that the metric tensor is written in this way, in this coordinate system, which is close to the Schwarzschild coordinate system, but R here is the radius of the two area, is not the necessarily coordinate, and it's possible to show that Einstein equation, which is, remember, the epsilon is the energy density and P is the pressure for our fluid, Einstein equations can be written as a set of these equations. So the energy density is given by F prime as R square of R prime, P is given, is obtained by this expression, R dot is given by this expression, prime is basically derivative with respect to this coordinate, and dot is derivative with respect to time, to this time coordinate. The Bianchi identities relates this quantity and this quantity. An important quantity that in this discussion is the Misner-Sharp mass, which is basically defined in terms of the lapse function by this expression. It has a very physical meaning. It means that it's a quasi-local form of mass. So imagine that you consider some radius, coordinate of radius, and you ask yourself, what is, how can I define a mass enclosed in this radius? That's, in a sense, the idea of the Misner-Sharp mass is a measure of the local energy density at some given radius. Because we know that in GR it's not possible to have a consistent definition of energy, and the mass is, the only mass is the ADM mass at infinity. So let's specify now a question in the case of homogeneous dust. Therefore, we take for the interior of the star, because the interior we know is homogeneous, we take basically a Friedmann-Robertson-Walker metric, and in this case, Einstein field equation becomes the following. Here, the energy density is basically what? The energy density for dust, mass over volume, okay? Nothing really special, nothing fair. There is no pressure, so P is 0, and this must hold, of course. That's just a definition of this quantity. The Misner-Sharp mass is given by this expression. So what happens in this case? We can match, we can study this collapse in the case of homogeneous marginally bound dust, and we can have for, in this case, the density is given by this expression, the pressure 0, the equation of motion is simply given by this expression here. And you can see A dot is given by this expression. That means that A double dot is positive, which means that you will eventually end up in a singularity. And this is a simple solution, and this is basically the Oppenheimer-Snyder-Dutt solution for the collapse of homogeneous dust. Now, here the trapeze surface is defined by this condition. This condition is a condition that of the formation of the first null hypersurface at some coordinate radius, and for the exterior Schwarzschild matrix, this corresponds to R equal to M. So therefore, someone from the exterior will not see, will basically see simply the Schwarzschild solution, will not know that inside the whole business is that the apparent horizon is moving towards the singularity and eventually will meet with the coordinate singularity at some given value of time. And that is the time that here the apparent horizon will take to reach R equals 0. So that is a very famous result by Oppenheimer, Snyder is discussed in textbooks that I think did maybe before them, but it was recognized only a few years after. And what to do with that? So we have a problem, of course, the problem of singularity in GR, and now the proposal is the following. There are many proposals to solve the singularity problem. In most of the case, you will see some proposal of this type. So imagine that you write this, the Schwarzschild metric in this way. That is in Schwarzschild coordinate, okay? And what people have tried to do since many years, okay? This is Schwarzschild solution, this is singular. What people do is, okay, replace this M with some M as a function of R, which is something like M0 R square R cube plus some constant, for instance, different from 0, so that when we are a small radius, this is R cube, when R is small, this gives you a de Sitter core. Okay? That has been done basically by hand. Many people, that's Ivar model, Poisson-Israel model. I also have done some model like that. Okay? For very large value of the, I mean, you think that this constant has to be related to some quantum gravity scale, things like that. At very large radius, you are back to this solution. But the problem is that we don't have, you can play this game. You can put this solution and this modification of the Mistner-Sharp mass in the Einstein equation. You can compute your energy momentum tensor, and you can see what is your effective fluid description. But the real problem is that there is no clear way of obtaining a solution of this type from a Lagrangian. Okay? People have tried, but what they found is something very bad. Either you have to put some strange nonlinear electrodynamic things, or you have to invent some. It's a real problem. We don't know how to couple to the Einstein equation matter in a way that for large distance we get back ordinary matter, and at small distance we cure the singularity problem. Okay, you probably have noticed that this is a static metric. Maybe the solution is that we have to go to a dynamical. So we have to produce this type of non-singular black hole, this is a non-singular black hole, in a dynamical way. And that is what I'm trying to present in the second part of my talk. So let's consider a self-gravitating fluid of matter in the rest frame of the fluid, described by 4 velocity, mu equal -1. Okay? The fluid is characterized by some energy density, epsilon, some pressure P, and some rest mass density given by this expression. Here m naught is the baryon rest mass, n is the number density of particles, and we assume mass conservation. Nothing strange, nothing fancy. The local form of first principle of thermodynamics is this one, and we imagine that there is the fluid is non-dissipative, so this must be 0, so that at the end you have this relation between the energy density and the rest mass density. So let's imagine my matter Lagrangian is given by this fluid, so it's basically minus epsilon. You can derive the Einstein equation in this case by taking the variation of the number density from this Lagrangian, and it's not difficult to show that the n must be given by this expression, so that the variation of the Lagrangian is given by this expression. It's all very simple, and what you do, and here is the idea, which was pioneered years ago, first by Vyacheslav Mukhanov and Markov. Let's imagine that now we have a multiplicative coupling between the matter and gravity. So, in other words, if this chi is 1, this is standard GR. No? I'm just pulling out 1/16 pi g of the Lagrangian. Now imagine that this is this coupling is a function of the energy density of the system. And why? Why I want to do that? Because imagine that in some situation this chi can go to 0, and so there is no coupling anymore from this term and gravity. And in some cases it's constant. I want to see what are what happens in this case. So if this is constant, we are back to the Einstein equation. If this is not constant, Einstein equation with this T mu nu and that, and we all know. But if this is not constant, we have to take the variation of this term, and we take the variation of this term, we have this additional energy momentum terzo. Now we see that the new Newton constant is given by this quantity. Because if I would, but also I get also a cosmological constant. So if I add this multiplicative term in the Lagrangian, my new effective equation, matter equation, are given by this expression, where here is basically a new gravitational constant. So what to do now? And I have a Lagrangian framework. If I know how this gravitational constant changes with energy, then I can try to build a dynamical model of regular black hole.
So this epsilon, this energy, so this is some external parameter that is put in, or is it?
No, it's just a matter. Now, the moment is the matter of the energy density of a fluid. I have a fluid with some energy density, and epsilon is simply the energy density of the fluid. The only thing that changes is that there is a coupling here between the standard Lagrangian and geometry through this chi. Okay, and now you see basically that's the new effective energy density, that's a new effective pressure, and you can, that is what I was saying, G of epsilon is given by this expression, and the new cosmological constant is given by this expression. So notice that if chi comma epsilon is negative, the cosmological constant is really a de Sitter. So it can help me in producing a de Sitter core. That's the thing. That's the key idea. But the question is what to do with this G of epsilon. And here is where a theory of quantum gravity come into picture. So that is the most technical figure of my talk. this is taken by this recent paper, where we have used the flow equation, which I will not go into it because it's too technical, to study the running of G Newton as a function of the following quantities, of the function of the external momenta and the cutoff. So what is this? Imagine that we consider electromagnetic or QCD, okay, or electromagnetic coupling. We know that in terms of if we make electron collide together, okay, the coupling constant in Q and D is a function of the external momenta, and we know that increases in this case, okay? So in this calculation, this was the first calculation, where in this blue line, you compute the scaling of the external moment. So imagine that you are making some graviton and graviton collide together. This is the scaling of the Newton constant as a function of the external momentum of the graviton, which goes in this way. Now, the point is that the blue line and the red line have basically the same slope. So that means that you can either describe the system, the running of G, at k equals 0 and make P running, which is the external momentum, or vice versa, you can describe G as at P equals 0 as a function of K. So you take a beta function that you have computed from your system and see how it works, how it behaves as a function of the running cutoff. This is a very physical interpretation. At very high energy, you can say that K behaves as the external momentum. So if you do so in this case, it's not difficult to cook up this model, where G is 1 of xi epsilon. So if epsilon here, what is happening? That I'm saying that the Newton constant is asymptotically free in F1, in a sense, because if epsilon goes to infinity, this goes to 0. If epsilon goes to 0, if epsilon is 0, Gn is just Newton constant. And then we could calculate K and lambda, and this is the new modified version of the running of the internal radial coordinate, no? So notice the following, that you never reach the singularity here, because this will go to 0 only at t equals 0. So you have an eternal collapse, as my students always says, if you want, the collapse is delayed at t equal infinity, and the space-time is geodesically complete. So the question is, what happens at the stereo? For the stereo, we have considered matching across a comoving boundary. You can do this basically using the standard matching Israel Gauss-Codazzi Israel matching condition. You can write the stereo metric in this way, and you can compute what is the new Mr. Sharp mass. If you do so, I will avoid to go too much into the technical things. You basically impose that the continuity of the second fundamental form across the boundary, and after you do so, you get the following function for the Mr. Sharp mass. Okay, that is basically this function here, this M of R. You can see that for R very large, you are back to a constant. This is a constant, okay? And for R very small, it will be different from this thing. But for r very small, you already know that you will never reach the collapse. You will never reach the singularity. And basically that is the situation. Depending on psi, you can have two horizons here, and the space-time is singular, there is no singularity. The two horizons coincides, or something which is a scalar horizonless things. This is basically a sort of a de Sitter core, but without being de Sitter. But the key point in this discussion is that all what I have done has been derived from a Lagrangian. It's not something put in my hand. I have used a Lagrangian and I have imposed that there is continuity across the boundary. And this, in fact, you see, m for large value of m, this goes to a constant, and when m instead is very small, when r is very small, you have this quantum corrected form of the mass, and you can find the detail of this paper, of this calculation in this paper, which appeared last year.
So at some point you are making the relation between epsilon and r.
Exactly.
I didn't get it. Can you say that?
The epsilon and so here the only relation that here is here.
I see.
The relation with R is at the matching. So I have an exterior geometry here, and I match the you see what must happen is that at R equal, the radius at some t equal constant must be equal. These two must be equal here. The two intrinsic geometry that fixes the radius here. This must be equal to r square must be equal to this quantity. Otherwise, the radius of the two spheres are different. And the condition for f comes from the matching of the second functional of the extrinsic curvature, second fundamental form in these things, and then you basically get a unique answer to this thing, solution to this thing. So, and okay, so the nice thing is that what I've done I have used this idea basically. I have implemented this idea. What happens if I change this? Okay, there's nothing really serious. Suppose I have this model of running of G. Suppose that G goes in this way, goes to 0 faster now with energy density, then your f of r is given by this expression, and you still have a regular black hole. So the takeaway, C is an unknown parameter. We don't know. Exactly. For psi equals 0, you get back the Newton constant, as we know.
But that is not a function of position or anything.
C is, no, it's a number. It's a positive number.
It won't come outside the Einstein equation, it's outside Newton times vector. And Newton is now C as well.
Exactly. Actually, exactly. What is in the right hand side is here. This G is key epsilon comma epsilon, which exactly is on the right hand side of the Einstein equation. If it is, if this is a constant, if chi is constant, this gives you back the Einstein thing. Huh? Chi is inside this. Chi is here is not specified at the moment. It's very general, is some function of epsilon.
But that's also constant.
Epsilon is a function of the energy density. So it's not a constant, it's a function of time in this case, in this model. Then then basically in this model, if assume that G is this one, chi is given by this quantity, okay? This quantity here. And so if I use this model now of running G, then I have this model of F, and the limit for F goes to 0 is just the Sitter core.
So from asymptotic safety, where you do the article from coming from functionality.
Yes.
So G will have some particular structure.
Exactly.
So that structure also
Is this one? Is this one?
is the previous one that you told.
It's basically this red curve here.
I see.
This approximate of this red curve is this one.
This one. I see.
Okay. Where I use K is basically proportional like epsilon, something like that. Yes, epsilon depends on time because in the interior you see I solve this equation here, and epsilon depends on time through the Einstein equation. Here, let me see where is it written. This is A, and epsilon, well, I don't have the equation written, but epsilon is basically, okay, in the standard case, okay, epsilon is 3m over a cube. That's the standard case. Now the equation is a little bit different, but epsilon will depend on a, and a depends on time. So a will move in this collapse, in this model, but it will never reach 0. Yes, that is what will happen. Basically, what happens here, that if you are in this case, suppose that A is R is proportional to A, you know? So suppose you are here, then you go back, and you will reach the 0, but in infinite amount of time. So you will never, so that your space-time is geodesically complete. And yes, and here is changing psi, this constant. You have again 1, 2, or 3 horizons. Depends what you, what is the phenomenology that you want to choose.
So we plug this solution back into the action, and the action is finite.
Yes, yes, exactly. And then if I have other few minutes, and that before I finish, this is a new thing. What I'm trying to do is to embed this model in a Hordesky theory. If you have Hordesky theory, imagine you have a general model of this type. X is this scalar field. Here is the equation of motion for the scalar field. That's the energy momentum tensor. And that's P and the density and this thing. And the question is whether under which condition I have an asymptotic, a regular black hole in this case. Can I do the same thing which I've done with the scalar field? Fortunately, it's not so simple. Here you have some constraint, no? If you have a scalar field, the sound speed is given by this expression, and you want that to be positive, to have something which is classically, which makes some sense. So what I did, you write a general static. Now this is a static framework, not a dynamical framework. So I show that in the first part of the code, the take away lesson is, if G goes to 0 fast enough, we can get a regular black hole during the collapse. Now let's go back to the static problem, and consider this general Lagrangian. You write a general static spherically symmetric in this way, okay? And now R is the radius of the two sphere. The Einstein equation reads this way. in this way. And now you can imagine that the new effective Newton constant is given by this quantity. It's basically G0 P comma X, okay? Where P is your Lagrangian. And so this is Gn, and then you can try to, I mean, that's, I don't have a, I mean, that's something totally new, okay? Let's imagine that our coupling constant goes, is a function, this function. So this, imagine that phi is very large, then G will go to 0. So can we cook up a regular black hole? Then in this case, your Lagrangian is this one, with phi is some potential, we don't know. A scalar field. Scalar field. Now it's, there is no asymptotic safety. I'm just imagine that G is some function like that, which you can think that if phi is very large, this G goes to 0. So intuitively, one can say, okay, large and positive values of phi will dynamically be suppressed or reduce effective coupling. Okay, you do so. And the equation, the Einstein equation for the problem I've shown you are this one. And now what I do, I make this assumption. So this is, I construct, that means that your spacetime is regular, because R will never go to 0. Okay? This is a positive quantity. So the question is, I want to reconstruct, I'm doing reverse engineering. I ask myself, if I do this thing, what is there any potential here which is physically sensitive, which makes some sense? So I do R, I write R in this way, and then this I can integrate this equation, and this is the solution. And A is a function of rho is given by this quantity, and you can see that you can have horizons in this case, because here A is 0, A is given, A is basically this quantity, so when A is a function of rho, it's 0, you have an horizon. So you can have horizons here and things are regular, but for large R, you are back to the Schwarzschild thing, and you can eliminate V phi, get an equation for R double rho, and this is phi as a function of rho from this solution. And in this case, you can get phi as a function of rho in this way, okay, which makes sense. And your potential is given by this expression in this way. And this potential, it's a nice potential. You see, V of phi is a function of phi as this form, so it's not crazy, this potential. So what I'm trying to show you is that I mean, this is a regular geometry, okay, which we can somehow try to believe as a regular black hole. And as before, the idea is to have a mechanism which kills the gravitational Newton constant at some high energy. Here, before you've done dynamical, this is done statically, and this is not published, so unfortunately I cannot give you more details than that one, but the conclusion of this discussion is that I think that regular black holes can be the outcome of gravitational collapse if G goes to 0 at high densities. We can cook up models which are regular, that comes from a Lagrangian, and have a regular interior, without the need of exotic matter. I have used dust. Okay? And then I derive the new effective field equation to do so. In principle, I could use a standard code for a collapse, and I could try to see whether I have a regular black hole or not in this case. And the other thing I would like to stress that maybe, but I don't have, I'm not totally convinced of that, we can cook up a static black hole solution with a scalar field by assuming that the effective Newton constant is dynamically suppressed in this way. But this is, let's say, this is a work in progress, so I will not insist too much on that. And what was before, it was already published. And so I think that I can stop here so I can take questions. Yes, yes. Exactly, but here I did reverse engineering, you know. I did not specify. I did this thing. I assumed that. I assumed this, and then I solve for the potential, because the potential is given by this expression. The Einstein field equation are this one. So where are the Einstein field equations? So you have this equation here, the equation for rho, and then from the Bianchi identity you have you can extract the V. So what I did, I assumed that I solve for A, and when I solve for A, then I here, because this I assume, I solve for phi, and then I get phi, and then the other last equation is the conservation equation, and that uniquely define V. It would have been better to have, okay, I have this V, which is whatever, and what is the solution? So that I could not do that. So, but at least it's promising. Maybe that it's worth looking at that. That is, yes, that is I checked that. That is positive all the time, yes. What happens is, the problem is that this is positive, but you can have ghost at the quantum. You cannot quantize this theory. Look here. This is G, okay? This for small, but depends on epsilon. For small phi is 1 minus phi epsilon. But this P it's in front of Lagrange, and this is the kinetic term. Okay, so so there is a price that you are paying. You have to have a theory which, if you are not careful enough, may produce ghost. So it's stable at the classical level. So let's say, it's an interesting chess game. You lose something from one side and you get something from the other side. So I have to be careful. But it's one understand a lot of Einstein theory working with this kind of models. A large energy density, yes. Large momentum, the same, yeah, right. Any? No, because goes to zero very slowly. That's true, but this, look at A. A goes to zero in this way. So it is zero only at t equal infinity. So before t equal infinity, okay, this is, you will not see any effect. So in any case, in other words, during this evolution here, suppose that you are here, no? The A passes the horizon, then it goes to, and then it's slow, but it never reaches zero. But here you have dynamical effect. The collapse is there. It will not hit the singularity in a very strong way.
So the curve for G epsilon, the curves were the analogs to the beta functions in one of these physics?
Exactly. This is a solution. This is a solution of a beta function, let's say.
So
This one, a solution. You put some k square here, That's a solution of a beta function.
So I'm just wondering, like beta function requires denormalization in the quantum physics.
Yes.
How do you apply denormalization in the Einstein function? Like,
Because this theory is asymptotically safe. I use, I mean, you can explain this. I use the fact that there is a non-Gaussian fixed point for gravity, and this you can define the theory a non-Gaussian fixed point, and you can have the theory renormalizable. In other words, it's a non-perturbative renormalization.
like the number of coefficients are finite, you know,
The number of coefficients are finite, but I mean, to show you the physical thing is this phase of the idea of by Polyakov. Passing to the continuum theory, discussed we can use as a starting point of quantum theory. The problem here is renormalizable. The quantum correction diverge at very high energies, and the energy of the virtual particle can be arbitrarily high. A possible way out is to conjecture that the coupling constant in gravity is scale dependent and tends to zero at small distances. Okay? This anti-screening of the gravitational interaction is quite natural, since the larger is the cloud of virtual particle, the stronger the gravitational force is. Yes.
Already answered this question. Yeah, I should think of G, scale-dependent G, is a product of some quantum theory.
Yes, yes, yes.
Some quantum theory. But would that quantum theory have every discrete feature?
With the quantum theory?
Yeah. Normally, scale-dependent are logarithmic.
Exactly. But they are logarithmic in if the coupling constant is dimensionless. But now the coupling constant is not dimensionless. And therefore the divergence is not logarithmic, but is quadratic. In QCD, the divergence is clear, but I mean, but here, because of the dimension full of the Newton constant, the divergence is.
So if you look at the running of the coupling of Newton constant, so if you, for example, just namely compute the beta function of the Newton constant in the dimensional tradition, then that 1 plus epsilon term that we are getting, so that won't appear. But if you do it in a non-perturbative way,
Yes.
then that 1 over
Exactly, exactly. If you do perturbatively with the standard dimensional regularization, you will not see that. That's a problem also with the measure that you are using, and that's it.
So in the recent work, where this is a more technical one. So in the recent one, when they computed the running of the coupling, so they used directly the function RT or the second derivative of the function
The
RT?
second derivative. For that case, because we also compute the running from the fluctuations. That was terrible calculation. That's that was really a nightmare. Next year, maybe if you ask the question, I'll try to answer. At the moment, I don't know how to. At the moment, yes, I don't know. Charge you can add, but the moment you move outside the spherical, I don't think there is even Oppenheimer-Snyder collapse in rotating solution. So even the standard is, as far as you know, the general case.
So the metrics that are written, so the metrics are basically written in Lorentzian metrics.
Yes, everything is Lorentzian.
But this running of the coupling, they are computed using.
Yes, using, but exactly. But I think that there is after this paper, there is another paper from Manuel Reichert and Daniel Littim. They have done in Lorentzian, and the result is they use this Callan-Semantic regulator, but basically the result is the same. I mean, in the very deep V, if you do weak rotation, is basically should not be a problem. Weak rotation is a problem when you are close to the mass gap.
Yes.
But if you are far away, I don't see any problem.
Any more questions?
So is this statement somehow implemented in the fact that epsilon scales as 1 over Planck constant? Planck constant is a large entity.
Uh-huh.
The energy scale at which we are operating is much smaller than
Yeah, this Polyakov setting, yes. I think so, yes. I think he has in mind the nonlinear sigma model in the equal 3. That is also the same. In the nonlinear sigma model, the theory is not renormalizable at the perturbative level, but non-perturbative, you can renormalize the theory.
Any questions? So, if no questions, then
Thank you.